We'll go back to the first. Okay, so this is actually 2019, right? So in 2019, actually, you can see that actually the first question actually a 15 kilowatt 230 volt 3-phase Y connected 50 Hz 4-pole squirrel cage induction motor has a starting torque of 115% and a maximum torque of 187% of its rated load torque, neglecting the effects of stator resistance and rotational losses, and assuming constant rotor resistance, find the slip and speed at maximum torque. Assume proper data if required with proper justification. So this is actually directly from the 3-phase induction machine, right? And this is a standard kind of question. And in 3-phase induction machines, actually almost all the questions are more or less like this only. Maybe the numbers are different, but so whatever the aspects that are asked were different, but the analysis is more or less like this particular problem only. If you are able to solve this problem, mostly actually you understood that particular topic. And the second one is actually explain the operation of a 2-phase induction motor under unbalanced operation with the help of relevant equivalent circuit models and phasor diagram. If the applied stator voltages to this motor are V alpha and V beta in time quadrature, but unequal in magnitude, prove that the starting torque of this motor is same as that developed when balanced 2-phase voltage of magnitude square root of V alpha V beta is applied. So this is actually the concept of single phase machine. So this is actually single phase machine, but that single phase machine actually it is converted into 2 phases, because actually single phase machine directly actually it cannot generate a rotating magnetic field. So to make it a rotating magnetic field, we are using actually a 2-phase system. Got it? Yeah. Previous year questions actually, so the typing was already done, but the only thing is I have to make the PDFs and put it, and I am updating both 2020 and 21. Right? Yeah. And then actually, so this is a third question is a DC shunt generator running at rated speed of 1000 RPM can supply a full load current of 120 ampere at a nominal voltage of 105 volts DC. The no load open loop, right? No load characteristics at rated speed, nominal voltage is given by field current and the generated voltage that were given here. So for different values of the field current, actually the voltage that is going to be generated actually that was given. Now graphically determine the field resistance of the shunt generator for its operation at nominal voltage at rated speed as a ratio of its critical field resistance. If the total fixed losses, so rotational and the iron, are 600 watts, find the value of maximum efficiency of the generator, given that the generator operates at 85% efficiency in nominal conditions, right? So this is actually related to the open circuit characteristics of the DC generator, and this is a very standard kind of question we can say, right? And then actually show that the locus of the tip of the armature current phasor is a circle for a synchronous machine, either generator or motor, operating at a constant terminal voltage Vt and a constant excitation voltage EAF with a fixed synchronous reactance Xs. Draw the phasor diagram and show the circular locus of IA. So this actually there is something called, there is a popular terminology, that is the circle diagram of a synchronous machine. So that is a standard question, right? So if you notice all the questions whatever I have seen here, these are actually the standard questions directly from the textbooks, right? So there is nothing different, and in every textbook more or less you will find these questions, this kind of models only. So that means actually the paper is easier, that you need to understand, because actually you can expect the questions directly from the standard textbooks. And this is actually a magnetic circuit shown below consists of 2 sections of aluminum nickel cobalt, right? And so of length Lm is equal to 1 centimeter embedded in a core of high permeability, and the cross sectional areas of core, right, and air gap are equal. The air gap length G is equal to 0.2 centimeter has a negligible fringing effect, right? And this is actually the transformer related question, so, right? And if Alnico 5 material BH curve in second quadrature is linearly approximated, it can be given as below. So this is actually this is BH curve, right? So BH curve meaning the magnetic flux density and the magnetic field intensity. That curve actually we call as the BH curve, and this BH curve actually it goes to first quadrant, second quadrant, third quadrant, and fourth quadrant. So it's like a BH loop actually you might have seen like this, right? A kind of shape like this, right? Reverted back. But in this actually what was given is only the second quadrant part actually that was given in the BH loop, right? And then actually determine the slope of the load line for the problem, and hence determine the value of flux density BZ in the air gap, right? So based on this particular curve actually we will have to identify the air gap flux actually here we have to identify. So depending upon the permeability actually the magnetic nature of the material that is going to be dependent, and the mu value actually it was given as infinite for this particular material, and in between actually there is an air gap, right? And here actually you will have to identify the flux density, and based on that actually you can calculate the H value depending upon the graph, right? And this actually it is part of the transformer. So it is actually not the usual question, but this is a bit tougher question only, right? It's not that easy, and not that easy in the so it's not from the textbook, but the difficulty level is easier only, right? That's it, right? So one tough question and rest of the questions are easy questions out of 5 questions, right? And all the questions are from the standard textbooks only, that you can make a note, right? And this is actually in 2018, a squirrel cage induction motor has a starting current of 6 times the full load current, and at a slip of 0.04, calculate the line current and starting torque in per unit of full load values of for the following starting methods. One is the direct switching and star delta torque, right? So squirrel cage induction motor. So for starting squirrel cage induction motor actually we use certain techniques. So in induction motors actually we will use certain techniques so that actually you can limit the starting current. For that actually you have either direct switching, or this is also called as the DOL, and the second one is the star delta starting. So you will connect actually star and delta. So because actually earlier actually we proved in the star to delta connection 3 times the current difference is going to be there. So that's why actually if you wanted to control the current, then actually you connect in star, and there actually then actually you convert into delta. Depending upon the requirement actually you will convert. And finally actually our goal is to limit the starting current, because actually suppose actually if you are pushing the car, then initially if you wanted to push the car, it takes more effort for us to move the car. Once it was moved, then actually it is easy to move, right? So that's actually initially the motor needs to be started. It takes a lot of amount of the current, because the torque needs to be started initially. That initial torque actually takes a lot of amount of the current from the source, and that you will have to limit it. Otherwise actually it will burn the coil. So the wiring that is there in the motor actually it will burn automatically if the current is not limited. So once actually it is started, slowly actually it reduces the current. So it won't require that much of the current actually once it was started moving. So that's why actually you have to limit the initial current. For that actually we will use different techniques, and these techniques actually we will use, that is the direct online switching, star delta conversion in case of the 3-phase induction machines. The second one is actually, this is also that is the standard question from the textbook. The maximum efficiency of a 50 kVA transformer is 97.4% and occurs at 90% of full load at unity power factor. Calculate the efficiency at full load at 0.8 power factor and half the full load at 0.9 power factor, right? So this is actually the percentage of the load that was given for the rated capacity, and at different power factors actually it was asked to calculate, and this is the straightforward standard textbook question also. And this is a 400 volts DC shunt motor draws 30 amperes while supplying the rated load at a speed of 120 radians per second. The armature resistance is 1 ohm and the field winding resistance is 250 ohms. Determine the external resistance that must be inserted in series with the armature circuit so that the armature current should not exceed 150% of its rated value when the motor is plugged, right? And find the braking torque at the instance of plugging, right? So plugging is actually one of the braking technique. So if you wanted to brake the motor, right? So whenever actually we are moving on the train actually when we apply the brakes, it will generate a huge amount of heat and that heat actually it is a wastage. In electrical motors actually we have better techniques for braking. What we do is actually, suppose actually if the motor is running in one particular direction like this, you will apply, or actually you will change the connections of the motor while running in this direction. I will change the connection so that actually it wanted to run in the opposite direction. So for that actually, so earlier it used to move like this. We have applied a reverse torque electrically, then actually it will reduce the speed to 0 and try to start in the reverse direction. But actually we will catch the moment when it was started, when it was exactly the 0 speed, and we will hold a mechanical brake over there, right? Like this, actually, there is a better technique in electrical, and that better technique actually even it will be useful in generating the energy. So rather than wasting the energy in the form of heat, actually, we will try to convert that mechanical energy into electrical energy again to charge the batteries, right? So this is actually one of the better technique actually we will use, and in that actually there are different techniques. One of the technique is the plugging, and this actually we will use for the braking purpose, and that actually he has given a straightforward question. This is a standard question from the textbook only. And here a DC generator has an armature EMF of 100 volts, and when the useful flux per pole is 20 milliweber and the speed is 800 rpm, calculate the generated EMF. And with the same flux and a speed of 1000 rpm, so what is the generated EMF? With the flux per pole is 24 milliwebers and a speed of 900 rpm, then what is the EMF generated? So the same question actually it was asked in different scenarios, and this is also standard question from the textbook only, right? Yeah, that's it. So all the questions are actually straightforward standard questions and very easy questions. So only thing is actually he has to cover multiple aspects. As I said earlier, electrical machines actually is a very big subject because the number of concepts are actually very high. I think not lesser than 100 concepts will be there in total. So out of 100 concepts actually they have to select 5 questions. So that's actually they will change the questions here and there because actually multiple concepts. Plugging is a different concept, characteristic is a different concept, analysis is a different concept, performance analysis is a different concept, operation is a different concept, application is a different concept. But each machine actually it has its own aspects, all these things. All these aspects, whatever I have said, this is there for every type of machine. So that's why actually they can ask these questions actually at every location. So that's why actually this needs a bit of time to prepare. And this is actually in 2017. So a 15 HP 220 volts 3-phase 50 Hz 6-pole Y connected induction motor has the following parameters per phase. R1 is equal to 0.128 ohms, R2 dash is 0.0935 ohms, and X1 plus X2 dash is right and 0.496 ohms, and RC is equal to 183 ohms, and XY is equal to 8 ohms, right? And this is actually induction motor circuit parameters that were given. So the equivalent circuit actually we will draw for the induction motor, and that actually it was given with the circuit parameters, and he asked us to find out the rotational losses are equal to the stator core losses, hysteresis and eddy current losses for a slip of 3%, and find the current and power factor. So this is a standard question from the 3-phase induction machines. The following test data were taken on a 30 kVA 2400 by 240 volts 50 Hz single phase transformer. Open circuit test is conducted at 2400 volts and 0.3 amperes, and the power consumed is 230 watts. And short circuit test was conducted at 70 volts 18.8 amperes, and the power consumed is 1050 watts. Determine the primary voltage, real and reactive power input, and efficiency when a current of 12.5 amperes at 240 volts is drawn from the low voltage side by a load of 0.8 power factor lagging. So this actually it was given for 20 marks, and this is a standard open circuit and short circuit test of the transformer. So transformer testing actually we have it, and in that actually this question is a standard question. An industrial consumer is operating a 1 kilowatt induction motor at a lagging power factor of 0.8 and at a source voltage of 200 volts RMS. In order to reduce expenditure on power consumption, he wishes to raise the power factor to 0.95, lagging by connecting a circuit element in parallel with the load. The circuit element will be obviously it is a capacitor, right? Indicate the type of the circuit element, that is inductive or the capacitive, and find the value of the operating frequency when the operating frequency is 50 Hz. Find the value. He didn't mention what is that value, right? Maybe a typo. So maybe we will have to correct this, right? So if the operating frequency is 50 Hz, so actually I don't know what it was asked. Anyway, I will correct this one, right? But this is a standard question. It's not different from anything, and standard textbook question. So a 230 volts 10 HP DC series motor draws a line current of 36 amperes when delivering a rated power at its rated speed of 1200 rpm. The armature circuit resistance is 0.2 ohms and the series field winding resistance is 0.1 ohm. The magnetization curve may be considered linear. Find the speed of the motor when it is drawing a line current of 20 amperes. What is the developer torque at the new condition? So this is also a standard question for the DC series motion, right? Yeah, that's it. So this is a standard question, and this is also a standard question. This is also a standard question. This is also a standard question. All the questions actually, it was asked from different missions, but standard textbook questions only. So this is in 2016. What do you mean by V curves of a synchronous motor? Draw them showing the loading power factor and leading power factor and lagging power factor regions, right? So this is the V and inverted V curves are there, which are the characteristics of the synchronous machine, and that actually we will understand. This is a theoretical question and very easy question, right? And the second one is a 20 HP, 230 volts, 1150 RPM DC shunt motor has 4 poles, 4 parallel armature paths, and 882 armature conductors. The armature circuit resistance is 0.188, and at a rated speed and rated output, the armature current is 73 amperes and the field current is 1.6 ampere. Calculate the electromagnetic torque, right? So this is a straightforward question, right? And the second one is the resistance and the leakage reactance of a 10 kVA 50 Hz 2300 divided by 230 volts distribution transformer R1 equal 3.96, R2 is equal 0.0396, X1 is 15.8 ohms and X2 is 0.158, and subscript 1 refers to HV side and subscript 2 refers to LV side. And the transformer delivers a rated kVA at 0.8 power factor lagging to a load on the LV side. Find HV side voltage necessary to maintain 230 volts across load terminals. Also find the percentage voltage regulation. Voltage regulation, as I said earlier, so the same concept that will be used here. This is a standard question from the transformers. It is known that the stator core loss amounts to 1200 watts and the rotational losses equal to 950 watts. Moreover, at no load, the motor draws a line current of 18 amperes at a power factor of 0.089 lagging. When the motor operates at a slip of 2.5%, find the input line current and power factor, right? So this is also a standard question, right? Okay, so this is induction motion, 3-phase induction machine. So this is 3-phase induction machine. This is transformer, and this question is DC shunt machines, and this is actually the synchronous machine. So one question from each type of machine, but every question is a standard question. So to summarize, actually, I have gone through all these questions now, right? So what I get the feel out of this particular, all these questions in all the years, whatever I have seen is, so the questions are covered from each question from each of the machine. But as I said earlier, every machine is having multiple aspects or multiple concepts to understand. And that concept is actually not just 1 or 2, right? So every machine has actually not lesser than 20-30 concepts. So the question can be asked from any concept. So that's why actually, if you notice, the questions are non-repetitive. So none of the questions are repetitive, if you notice, right? So all the questions are actually, every year actually, the questions are asked from different concepts. So that's why actually you have to understand all the concepts, and then actually you have to prepare each and every aspect from the textbook. So that's why actually it's not that easy. As I said earlier, 100 concepts will be there, not lesser than that. 100 concepts, it takes more amount of time. Even for me also actually to take this entire subject actually usually not lesser than 50 hours it will take, not lesser than 50, right? Sometimes actually, so in gate coaching and all actually they do take actually 70 hours for this particular subject. I know that when I was taking gate coaching, that time actually I used to take around 70 hours to take up all these classes. But actually I will try to accelerate it and I will try to cover in 50 hours. But without leaving any concept, I will cover each and every aspect. And what is the best book to follow? Anybody? Yes? Which one actually you are more comfortable? You might have gone through, right? So Naik and Venu, you can comment which book you followed in your graduation. P.S. Bimra. Okay. What about you, Venu? P.S. Bimra. Right. So, but actually, so basically, I am from actually a diploma background, and then actually I did my engineering. In that case, actually, I have studied these electrical machines actually initially when I was in diploma itself. So there actually we used to follow BL Teresa, volume 2, that is the second. And then actually that is actually very, very low level book. And at graduation actually I followed PS Bimra only. But actually Bimra actually not all the people are very comfortable, PS Bimra. So that's actually you will face a bit of difficulty in understanding Bimra sometimes, right? So if you are already expert, actually you won't face any difficulty, because actually the wording and the concept, the way they explain actually is a bit difficult, right? But actually I suggested a different book I found actually recently, right? Exactly, right? So Ashish, I was about to tell that only. You try to follow this particular book, that is Aswak Hushan, this book. And why I'm suggesting this book is actually it's not difficult like Bimra, and it covers all the concept at an easier level. It is actually higher than BL Teresa, lower than PS Bimra. And this book actually I find it much more comfortable, and all the concept or actually all the questions also actually you can notice from this book only. Actually you can notice the UPSC previous year questions also. So that's actually you follow this book and you will be easily understanding each and every concept once I explain, right? Even on your own also, if you study, you will be able to find it very easy to understand this book. But PS Bimra is not like that, right? Not all the people may not be able to understand, right? So when I was studying graduation, I followed only PS Bimra. So, right? So if required, actually any other book I will explain, but otherwise actually by default only follow this particular book. And so trust me, it will accelerate your preparation if you follow this particular book. Got it? So on top of that, if you have any questions, you can always ask me. So that's not a big thing. And I have actually PS Bimra old book, and this is actually very bulky book. But actually understanding is actually more of a research level. So this book is more of research level. So that level of knowledge is anyway not required for us. Okay. So Venu, I didn't get you. Yesterday optional paper meaning? Okay. That actually you will get it in this one, right? So in UPSC website actually you will find it. You will be able to download. Right. So if anybody actually wrote the exam, then actually they will be sharing it, or else actually in UPSC they will update it. Fine. Right. Okay. So I have covered the syllabus. I have covered the weightage and what are the books to be followed, and approximate number of hours also I have covered, and the previous year questions also I have covered. Any questions on this? You can ask me. Any questions? Okay. Fine. So first actually let us understand the basics, right? So first actually we will understand what is meant by torque. So all of you people are aware of what is meant by torque. But actually when I was studying my graduation at that time, actually it was very, very confusing for me. So did you people understand what is meant by torque? Okay, so let me explain the meaning of this torque. Suppose actually if there is a block of mass like this, on this actually if I apply a force like this, then this force actually will try to move this particle in this particular direction. So this block actually is moved in this particular direction if you apply a force, right? So that means the force actually is corresponding to the amount of the displacement. Obviously, it will accelerate the particle, and the acceleration will generate a voltage. So the acceleration will generate a velocity, and that velocity will cause the displacement. So this is how actually it works, like Newton's laws, right? So this is the force. And then actually, if I ask the question, so what is the twisting force? That means actually, here actually, this is a linear force. Linear force meaning because of the application of this force, it will cause a linear displacement. So from this particular position to this particular position, actually it was moved. So this is a linear displacement. But what I wanted to do is, suppose I wanted to keep the block as it is like this. This is the block. I don't wanted to change the display. So this is the center of mass of this particular block. And then actually I wanted to rotate this block like this. So now in that case, actually, does the location of the center of mass is changed? Right? The center of mass is actually not changed. So, but that doesn't mean that actually it's not moved. It is moved, right? So it is moved, but the center of mass is not changed. And this also happens because of the application of the force. Suppose actually if I apply the force like this, then actually it will try to rotate. Now, this rotation actually is not just dependent on the force, rather than the force, along with the force, there is one more component. At what distance you have applied this particular force? You might have applied here, or you might have applied here, you might have applied here. At what location the force is applied with respect to the rotational axis. So this axis that is vertically coming out of this particular block is called as the axis of rotation, because actually the block is rotating like this. Now in this case, actually this line, that is the pen, actually is the axis of rotation. So with respect to the axis, how far actually you have applied the force, both of these values, this R value and this F value together will decide how much it has to rotate. So that is torque is equal to R cross F. And that means force and the distance together where it was applied will decide amount of twisting force. So this is called as the twisting force. Right? So amount of twisting force actually is dependent on two different aspects. And so that is, so here actually force, and the force actually will create a linear displacement. The torque will create a angular displacement. Got it? So linear displacement and the angular displacement. That means whenever we wanted to analyze the mechanics of any particular body, we will have actually one is the force, and here actually the torque, equivalent of that. But the difference is creates a linear displacement. And creates an angular displacement. Meaning, suppose if there is a block here, and this block actually is moved to this particular place, and this is the center of mass, this is the center of mass, so this is the displacement x. And here what it will do is, suppose actually there is a rod like this, and this rod actually it is moved to like this. So initial position is this one, and the final position is this one, and here actually there is an angle in between these two. This is called as the angular displacement. So every particle actually is moved by an angle. Now, if you take this particle or this particle or this particle, all these particles move the same angular displacement. That means move the same angle, but the length it was moved is different. So this length is different, this length is different, this length is different, this length is different, and this point is actually not even moved from that particular location. So that is as it is there itself. So here actually it is maintaining the same angle, but different particle actually move different angle, different displacement. But in this case, if you notice, if I take the top corner, it is moved to the top corner here, it is the same displacement. If I take this bottom corner here, it is the same amount of the displacement it is moved. Every particle of that block actually is moved the same amount of the displacement in case of the linear displacement. But in this particular case actually, so every particle actually will be having a linear displacement differently, but the angle is same. So every particle moved the same angle. So this is called as the angular displacement. And this is usually represented as x, and this is usually represented as theta. And obviously actually here we have the linear velocity. So linear velocity, the popular name is simply the velocity. And this is the dx by dt. And this is the velocity v, and which is a vector here. And same is the case actually we have the angular velocity. Angular velocity, and this is usually represented as omega. This is also a vector, but it is a rotational vector, and d theta by dt. And this is actually in the theta cap direction. So the polar coordinates, whatever we are using, so that is actually the theta cap direction. You can notice the velocity of the particle, right? And here actually the acceleration. So acceleration a is So dv by dt, and this is the acceleration. Here the angular acceleration. Alpha is equal to d omega by dt. So this is the angular acceleration, and this is the one, right? And so, and here actually we have the energy. So kinetic energy is equal to half mv square, and this is the kinetic energy generated in moving the particle because of the velocity. And here also actually we have the angular velocity, and that angular velocity actually it will generate the angular kinetic energy, right? So the energy is actually, it is not having any particular direction because that is a scalar quantity. And here actually the equivalent value, the kinetic energy in case of the rotation is half I omega square. Half I omega square, where I is the moment of inertia. So the same kind of formulas actually you can notice the linear and angular, right? So whenever there is an angular analysis or actually the angular rotation analysis, then actually we will be talking about the cause is the torque, and it creates an angular displacement theta, and it creates an angular velocity omega. So angular omega, so this is even be called as, see this omega actually is the angular velocity which is given by d theta by dt. But actually every 2 pi radians actually it will create one rotation. That means suppose the angular velocity is divided with 2 pi, then so this is the displacement actually, it is divided with 2 pi, then obviously actually it will be the rotations per minute, rpm. So the time is taken in minutes, and the angle is actually taken, instead of the angle theta, we can make into number of 2 pi's. Each 2 pi actually it will create one particular revolution. So that's actually rpm we always talk about, that is the revolutions per minute. So the rotational velocity we are going to take it rather than d theta by dt. Instead of that we will have the rpm, right? And this is the torque. Now this torque actually you can even measure the torque. Suppose actually, see this, whenever we talk about the cross product in vectors, right? So cross product in vectors, if you notice, so suppose actually there is darwaja, right? So this is actually the door. Then actually we will keep a hook at this particular point to open this particular door. And what we wanted to do is, suppose actually if I keep the hook here, then actually will you be facing difficulty in opening the door? Yes or no? If I keep the hook here rather than at this particular end, so are you facing the difficulty in opening the door? Yes or no? Obviously, right? There is a very, very difficulty you are going to face it if you wanted to open the door. Obviously, you can't even open. And if you keep on shift this hook to this particular place, then actually you will find a little better. And if you keep it here, you will find a little better. If you keep it here, you will find a little better. If you keep at the extreme end, that is very easy for us to move, right? Now, here we are talking about, this is the axis of rotation. This is the axis of rotation. And then actually, this is the radial distance where you wanted to apply the force. From the axis of rotation, this is the radial distance where you wanted to apply the force. And then actually, you are applying the force like this. So this is the force direction actually what you have given. Now, in this case, suppose actually, I can even keep the force exactly perpendicularly like this, or actually, you can even apply the force at an angle like this. So in any direction, actually, you can apply the force. But actually, that force may not be 100% useful for us. Only the component of the force that is exactly perpendicular to this particular door is useful for us. Because actually, it is very easy for you to move the door if you apply the force perpendicularly. So even though if you apply the force at an angle of theta, then this component of the force is f cos theta. And exactly perpendicular to this, actually, it will have f sin theta as the force. And that f sin theta is useful in moving this particular door. So the torque is consisting of where you are applying the force and how much you are applying the effective force. I am applying the force at a distance of r, and the effective force what I'm using is f sin theta. So r into f sin theta is the torque. Got it? So that is essential deciding how much twisting force actually I am able to use it. How much twisting force I am able to generate, that depends on where I have applied and how much I have applied. I applied the force F but an angle of theta. So in that case, F sin theta is the useful component, and this is actually popularly we call this as R cross F, R into F into sin theta. Now, why this is a vector is the force if I apply onto the forward direction, then actually the door will rotate in the other direction. So that direction we call this as the anti-clockwise direction. So the door is moving inside. That is, with respect to this vertical line, you can draw a line like this, which is in the anti-clockwise direction. But if you apply the force in the opposite direction, then actually the rotation is actually the clockwise direction. So the clockwise direction it is going to be there. That's why this torque actually depending upon the force. If it is the plus force, then actually it is inside. If it is minus force, it's in the opposite direction. Both the directions needs to be separated. That is why actually we use this torque as a vector, but only two directions, right? Only two directions for this particular torque. So one is the clockwise and another is the anti-clockwise. Right? Anti-clockwise we usually treat as plus, and clockwise actually we usually treat as minus. Got it? And this is how actually we calculate the torque. And this torque is actually very, very useful in the analysis of the electrical machines, because you wanted to measure the amount of the mechanical energy that is going to be generated. Now, to measure the mechanical energy, what you wanted to measure, how much torque you are able to generate by giving an electrical connection, right? So the motor capacity is how much torque it will be able to generate. That's exactly what you wanted, right? So similarly, how much torque if you give it to the generator, how much energy it is going to generate. So that means you are giving the mechanical torque and it is generating the electrical energy. And if you give the electrical energy, it is generating the mechanical torque. It's not the force. Nowhere we talk about the force in case of electrical machines. We always talk about the torque. Torque means twisting force. And that is dependent on the radius and the force, how much it is going to be generating. And this torque actually we will use for the analysis purpose. Got it? I hope you understood the concept of this torque. Right? So one of the very, very important thing is actually the moment of inertia. So moment of inertia actually, it is a physical quantity that was defined just for the analysis of the rotational equipments, and by taking the advantages of linear equipment analysis. That means linear actually we tried mapping it. So displacement, angular displacement, velocity, angular velocity, acceleration, angular acceleration, torque, force, everything is actually we have mapped, right? And we have actually other formulas also. Like actually we know that actually F is equal to ma, there is a formula. Then in the similar way, F is the force, the equivalent is torque. So T is equal to mass actually is equal in term to moment of inertia, and the acceleration is A and angular acceleration is alpha. So wherever mass is there in case of linear analysis, the corresponding component is the moment of inertia. Half mv square and half I omega square. I is replaced with m there, or m is replaced with I there. So what is this? So this moment of inertia is defined just for the purpose of making these two exactly equivalent for the analysis purpose. Only that purpose we have defined the moment of inertia. But how to calculate the moment of inertia is, so that is actually when we wanted to calculate the kinetic energy. Suppose actually if I have this particle like this, so this is the block of mass and actually it is moving like this. Now every particle will be having the same amount of the velocity. So half mv square, if you wanted to calculate which is the kinetic energy of this particular block while moving from this location to this location, every particle, if I do it, every particle actually it is having m1 square v1 square, m2 square v2 square plus dash 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 mn square vn square, half of. And every particle kinetic energy, if I make this particular block into n different particles, the sum of the kinetic energies is the total kinetic energy of this particular block. Now, this one actually, every particle is having the same velocity, hence actually we will take it. So this is half m1 square plus m2 square plus dash 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 mn square into v square, right? So now actually every individual particle actually is squared and added, and this is equivalent to half, so m square, total m, sorry, half mv square, right? I took the formula wrong. m1 v1 square m2 v2 square plus dash 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 mn vn square. Now the v value is same for all the particles, hence actually this is m1 plus m2 plus dash 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 mn v square, and the sum of all the individual particles mass is the total mass, so half m v square, and this is the kinetic energy of the block if it is moving with a linear velocity. But the same thing actually you wanted to bring for the rotational moment. So that is actually, it's not that easy like this. What we do is, suppose actually if there is a rod like this, and this rod actually when it is rotated like this, and let us say actually we have a particle m1 here, m2 here, m3 here, dash 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 mn here, right, mn. Now if this is moved like this, then in that case you wanted to calculate the kinetic energy. So the kinetic energy in case of rotational is equal to half m1 v1 square half m2 v2 square plus dash 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 half mn vn square. This is the total kinetic energy. Now half we will take it out, and then actually m1 into, now let us say this is the m1 from the axis of rotation, so this is at a distance of r1. Similarly this one actually which is at a distance of rn, right? So mn particle is at a distance of rn. Now this particle actually is rotating like this, and this particle is rotated like this. So because actually this is how actually it was rotated after some time. Now in this case every particle traveled different displacements within the same time. So this is moved like this. Within the same time, every particle of this block is moving a different amount of the displacement. I hope you understood that, right? And this distance is equal to, so this length L is equal to r into theta. So this is the arc length of the circle, which is given as, if the angle of rotation is theta, then this arc length is equal to r times of the theta, where r is the distance. Now you wanted to calculate the velocity of this particular particle, so that is the Vn is equal to, so d by dln by dt. So this is the velocity of every particle. So this arc length, with respect to that actually we are taking the time derivative. Then this value is Vn is equal to d by dt of Rn into theta. Theta is same everywhere. So this is theta into drn by dt, right? So that is actually the velocity, and right. So what we will do is, we will try to consider the particle velocity, each and every individual particle we take it, right? And half mr or mi, one particle. So mi, and then vi square, mi vi square sigma. So this is actually the total kinetic energy. I am putting in a shorter form. Sigma mi square vi square. Now this vi value for a particle, ith particle actually you take it, and this is at a distance of ri, right, ri, and the mass of this is mi, and actually this is moving like this. And if you want to calculate the velocity, so vi is equal to, so d by dt of ri into theta, right? So ri into theta, so this is so ri into d theta by dt. So this is ri into omega. So this is actually the velocity. So we actually popularly know that actually that is the linear velocity is this velocity. Linear velocity v, which is always equal to, so the radius multiplied by the angular velocity omega. So this I think you might be already aware of it. So v is equal to r into omega. That's exactly actually what we have done here. Now what we do is, so half into sigma mi into ri into omega whole square. So this is half sigma mi ri square. Omega is same for every particle, because actually every particle is moving the same amount of the angle. D theta by dt is same for everywhere. So then this is omega square, we will keep it. And this actually we have given a separate name, that is where I is equal to sigma mi ri square, and this is the name is the moment of inertia. And this moment of inertia is different for different shapes. So if the shape of the body is different, the moment of inertia is different. And similarly, so the orientation of axis, suppose actually from this actually if it is rotated like this, then the moment of inertia is different. With respect to this point, if it is rotated like this, the moment of inertia is different. So the axis of the rotation and the shape of the body together will decide the moment of inertia of that particular body. That means moment of inertia is not the characteristic of an external aspect. That is velocity, actually if you apply the force, actually it is going to be generating the velocity. But the moment of inertia is decided by the particle orientation. Mass is not like that. Mass actually, this pen actually if it is there, this pen actually having certain mass. It doesn't matter actually if I keep it like this, or if I keep it like this, or if I put it here, it is having the same amount of the mass. But the moment of inertia is not like that. If this mass is rotated like this, it will have a different moment of inertia. Rotated like this, actually it is having a different moment of inertia. Rotated like this, actually it is having a different moment of inertia. So the moment of inertia is dependent on the axis of rotation, and also the shape and orientation of this particular mass also is exactly depends on the moment of inertia. Got it? And these are the aspects that you have to be aware if you wanted to talk about the torque. Right? We always calculate the torque in the machines. Got it? Any questions? Is this clear? Okay, fine. So with this actually I would like to stop the class for today, and tomorrow onwards actually we will start the DC machines first, and then we'll proceed from there. Yeah, that's all. Thank you.